All right, let's dive into a concept that's so fundamental we barely even think about it, motion. But what does it really mean to be moving? And how can we even be sure? Well, we're about to find out.
So, I want to start with a question for you, right now. Wherever you are, whatever you're doing, are you moving? Your gut reaction is probably, no, of course not, I'm just sitting here. But here's the thing. In the world of physics, you're kind of both right and also very, very wrong.
See, in physics, motion is never this absolute, clear-cut thing. It always depends on your point of view. And that one simple idea, it's the key that unlocks, well, pretty much everything else we're about to explore.
Before we can even begin to measure something that's moving, we first have to anchor ourselves to something that we can all agree is still. And this is where we discover the secret ingredient to observing the universe, the reference frame.
So, what is a reference frame? Honestly, just think of it as your anchor point. It's the background scenery you use to judge whether something has actually changed its position. Without a reference frame, the word motion is, well, it's pretty much meaningless.
Let me give you a perfect example. Imagine you're sitting on a bus. If your reference frame is the bus itself, the person sitting next to you isn't moving at all, right? But for someone standing on the sidewalk, their reference frame is the ground, and from their point of view, you're both zooming by. It's the same person, the same actual movement, but two totally different realities. It's all relative.
Okay, so we have our anchor point, we have our reference frame. Now, how do we actually measure the movement that we're seeing? Well, physics gives us two completely different tools for this. One measures the entire scenic path, and the other just takes the shortcut.
First up, we've got distance. This one's super intuitive. It's your step counter, it's the odometer in your car, it is the total ground you cover, adding up every single twist and every single turn of your journey.
Take a look at this image. You see that long, winding purple path? That's the distance you traveled. It's the actual route you took, with all its zigs and zags. It's the full story of your journey.
But then, there's displacement. And displacement is, well, it's brutally efficient. It doesn't care about the scenic route. It only asks two simple questions. Where did you start and where did you end up? It is the straight line short part between those 2 points. That's it.
So, let's put them head to head. Distance is the total path you took. Displacement is just the shortcut. If you're moving, your distance is always getting bigger. But your displacement? Get this, it can actually be 0. Imagine you run a full lap on a track. You've covered a lot of distance, right? But you ended up exactly where you started, so your displacement is 0. Nothing. This difference is a huge clue about something else.
And that's the difference between a scalar and a vector. A scalar quantity just gives you a number, a magnitude. Think 5 kilometers. That's it. But a vector quantity, it gives you the whole story. It has both a magnitude and a direction. Not just 5 kilometers, but 5 kilometers north. See? It's a massive difference.
Okay, so we know how to describe the path. But what happens when we ask, how long did it take to travel that path? Well, as soon as you add the element of time, you take this to a whole new level. Now we can start talking about how fast things are really going.
Speed is a word we use every single day, and it's simple. It's just the distance you've traveled divided by the time it took. And since it's based on distance, our scalar friend, it only tells you how fast you're going, not where you're headed.
Velocity, though, is the vector version. It's not based on the total distance. It's based on displacement, that straight-line shortcut we talked about. This makes it way more precise because it tells us not just how fast we're going, but in the exact direction that our motion is happening.
So what's the difference in the real world? Think of it this way. Your car's speedometer tells you its speed, 60 kilometers per hour. But your GPS, your navigation app, it needs your velocity to work. 60 kilometers per hour east. One is just a number. The other is a number with a purpose, with a direction.
So we can describe a position, and we can describe how fast that position is changing. But what happens when the speed, or the direction itself, starts to change? That brings us to the most dynamic piece of this whole puzzle.
This is acceleration. And here is the absolute key takeaway. It is not just about speeding up. Because velocity is a vector, right? It has speed times direction. So any change to it, speeding up, slowing down, or even just turning a corner while maintaining the same speed, all of that counts as acceleration. It is the measure of change itself.
And here's how we calculate it. It's actually pretty simple. You take an object's final velocity, you subtract its starting velocity, and then you just divide that whole thing by the time it took for that change to happen. And boom, You get a precise number for just how quickly the motion is changing.
Now, I know this might all seem a little abstract, like something on a physics classroom chalkboard. But the truth is, these concepts are running the world around you every single second. So why does all this really matter?
You see this stuff everywhere. Every time you glance down at your speedometer, you're looking at instantaneous speed. The GPS that's navigating your road trip, it's constantly calculating your velocity. I mean, everything from a simple bouncing ball to the massive, steady orbit of the Earth is just a beautiful dance of displacement, velocity, and acceleration.
Which brings us right back to our very first question. You are on a planet that's spinning, that's orbiting a star, in a galaxy that is hurtling through the universe. So I'm going to leave you with this to think about. If everything is moving relative to everything else, is there any place, any single point in the entire cosmos that is truly, absolutely standing still? Something to chew on. Thanks for tuning in.